Hi, I am Aditya and I am the CEO of Automatski. Automatski makes the most powerful quantum simulators, annealers, and computers in the world. Today I am going to demonstrate random walks to you and I will keep it extremely short. I assume you already know the theory and applications, and I also assume that Automatski has given you the context of this video. So you will understand what I am going to show you. If you receive this video by mistake and don't know what this is all about, just ignore it. I'm here to tell you what we have achieved and not how we have achieved it. All our millennium breakthroughs are completely our own inventions without any collaboration or help from absolutely anyone else. The implementation details of our inventions will remain a secret for the next 1,000 years. If that doesn't work for you, you should stop watching this video right now. Now, people talk about random walks, quantum walks, classical walks. They talk about walks on a line, on a circle, on a lattice, and so on. But the toughest problem to solve in random walks is to solve it on an arbitrarily connected graph, and that is what we're going to show you. Now, quantum walks are quantum analogs of classical random walks. In contrast to classical random walk, where the walker occupies definite states and randomness arises due to stochastic transition between the states, in quantum walks, randomness arises through quantum superposition of states, non-random reversible unitary evolution, and collapse of the wave function due to state measurements. As with classical random walks, quantum walks admit formulations in both discrete time and continuous time. So today I'm going to show you both discrete time and continuous time random walks, but I don't have a application or a use case which can show the difference between the two, and so I'll leave it at that. Now, quantum measurements are a exponential disadvantage. Quantum state preparation is also an exponential disadvantage. And for a quantum walk, the graph becomes exponential in size. Nobody talks about these things. But finally, we think we have solved the problem of random walks by achieving exponential advantage, and we have done this deterministically. This is very, difficult to understand how we can do this deterministically, but I'll leave it at that. Probably I'll explain it when we talk face to face. Remember, classical and quantum walks are stochastic. So solving it deterministically is a major breakthrough, and solving it in a fashion that gives a confirmed exponential advantage is also a major breakthrough. Let me get started. So we have a small graph of 20 vertices or nodes or whatever, and we don't have any starting position, so we keep it null, and there is another parameter, ignore that. So let me run it. Okay, now I have just printed the vertices and the distribution. So this is in a way the limiting distribution of the aggregate walk on the graph. Now so once we understand this, I like to show you how we can scale to large problems. For us at Automatski, we call problems of 1 lakh or 1 million nodes or qubits as mid-sized problems. We scale our systems to 100 million, 1 billion, and in some cases 1 trillion qubit problems also. But our production systems will be 1,000 times faster and 100 times more costly and literally accurate, cent% accurate. This is currently running on a test environment which is 100 times cheaper and 1,000 times slower, and it is also not very accurate. So the probability distribution will have some variations. But that said, all our systems are remotely hosted in our data centers and offered as a SaaS service. You can program them in multiple languages like Java, Python, Rust, or Mojo, or whatever. So that is not an issue at all. Let me now come to bit scale problems. Let me run 1,000 vertex problem. So you see this, it is executed. It's even the test environment is really fast for such small problems. Now, for large problems like this, 1 lakh vertices problems, we will not be able to render the graph because it doesn't actually make any sense, but it is also difficult. So let's see. This is a discrete random walk on an arbitrarily connected graph with an exponential advantage, and it is going to converge. It took 16 seconds. It will not render the graph because with 100 vertices it is difficult. I'm going to stop this. Similarly, for a continuous random walk, I'm going to show you a small problem with 1000 vertices. And it almost does it instantaneously. Okay, to understand the technical differences between discrete and continuous random walks, you can look up the literature. That's all we had for today. If you have any questions, you can email us at info@automatski.com. Thank you very much.